Welcome back, everybody. We're going to continue on with the notes for week 1 of your online learning, part 2. So in the first video, we went over how to calculate heat with Q equals mc delta T, and how to calculate heat when a phase change is occurring, which is Q equals N delta H of the phase change. So we can put both of those things together and look at what's called a heating curve. So we know the freezing point is when the liquid's converted into a solid. We know the melting point is when the solid's converted into a liquid. You know, the boiling point is when the vapor pressure equals the atmospheric pressure. And so you're going to go from a liquid to a gas. Condensation point, the temperature in which a vapor has lost enough energy in order to turn into a liquid. The freezing point and the melting point, oops, that's not annotation. The freezing point and the melting point are at the same temperature, just like the boiling point and the condensation point are at the same temperature. And again, it all has to do with, is it going in or is it coming out? If energy is going in, it's melting. If energy is going in, it's boiling. If energy is coming out, it's freezing. If energy is coming out, it's condensing. So just keep in mind that those are at the same temperature that those things occur. Now, how a heating curve works, you can see the diagram here. Temperature on the y-axis, time on the x-axis. So what happens, let's say this is for H2O. I take a big beaker, I put a bunch of ice in it, I stick a temperature probe in it, I put it on a hot plate and let it go, and this is what you see. Now, from A to B, I'm going to have nothing but a solid. So I stick my temperature probe into the ice, I increase the temperature of that ice until and it's just a solid until I get to point B. Point B would be the melting point, the point in which it starts to melt. And then from B to C, you can see that the line is flat. It's very important. Temperature remains constant during the phase change. All of the energy goes into changing the state. And so the line stays flat and you have both a solid and a liquid until point C, when you have nothing but a liquid. Then the temperature can increase until you get to point D. Once you have all liquid at the right temperature, that would be the boiling point. And then from D to E, you're going to have a liquid and a gas until it gets all gas, and then the temperature can increase. So when you're going from A to B, when you're going from C to D, when you're going from E to F, you'll notice there is a change in temperature, and therefore you must use Q equals mc delta T. When you are from B to C, when you're D to E, that is a phase change. And therefore you have to use Q equals N delta H of the phase change, whichever phase change that you're going through. Right? So make sure you're paying attention to that. So let's do some calculations. So we can read this question here. It says, how much heat in kilojoules are required to heat ice at 15 degrees Celsius to steam at 127 degrees Celsius? Well, first off, at 15 degrees Celsius, we are not ice. That should be water, obviously. And it doesn't give us an amount. So let's say 100 grams. So we have multiple steps that we need to do here. So for step 1, we need to take our 15 degrees Celsius and we need to go to 100 degrees Celsius. And that's going to be Q equals mc delta T. And then what happens at 100 degrees Celsius? Well, step 2, that would be the phase change. So the phase change at 100 degrees Celsius. And then the third step to this question to calculate how much heat would be going from 100 degrees Celsius to 127 degrees Celsius. And again, that would be Q equals mc delta T. Something important to note. For the first step from going from 15 to 100 degrees Celsius, we're using Q equals mc delta T. That's water, so we use the C of water which is 4.184 joules over grams degrees Celsius. For the third step, when we're going from 100 to 127, we need to use the C of steam, which is written over here, 2.03 joules over grams degrees Celsius. Once we do each one of those steps, we make sure they're all in the same unit of kilojoules because that's what the question's asking, and then we can add them all up and that will give us our answer. So I'm going to erase this so I have more room to write. And again, feel free to pause this at any point. You need to write stuff down, rewind so that you can get everything that you need. So we'll start with the first one of Q equals MC delta T. And so we're going to do our 100 grams times 4.184 joules over grams degrees Celsius times, we're going from 100 to 15, or sorry, 15 to 100. So we do 100 minus 15. And that will give us, when we put it in our calculator, 35564 joules. I'm going to convert those into kilojoules and put it into the correct number of sig figs, which will be 3.6 kilojoules. So that's step one. Step two is doing the phase change. So we need to take our 100 grams, turn them into moles. That should be fairly simple. It's going to be 5.556 moles H2O. Now we are vaporizing, so we're going to go to the delta H of vaporization, which was on the previous page, which is going to be a positive 40.6 kilojoules per mole. And so then we can just take our 5.556 kilojoules, multiply 40.6 kilojoules per mole. And so we will get with the correct number of sig figs, 225.6 kilojoules. And then the third step is going to be Q equals MC delta T. But now I'm steam, so I'm going to use the C. So Q equals, we're still with 100 grams, times 2.03 joules over grams degrees Celsius, times, and then the change in temperature, 127 minus 100. Add that up. 5481 joules. In sig figs, in kilojoules, 5.5 kilojoules. So I've got my answers from each one. And now my total heat is just going to be those added up, which gives me 234.7 kilojoules. So that's how much energy is required to heat water at 15 degrees Celsius into steam at 127 degrees Celsius when I start with 100 grams of water. I'm going to clear this. So that combined my Q equals MC delta T, my Q equals N delta H equations, and we can put those together for a heating curve calculation. Next thing we're going to look at is thermochemical equations and energy diagrams. A thermochemical equation, we've seen these before. It's just a balanced chemical equation that has heat as either a reactant or a product. So in this case, this is going to be an exothermic reaction because energy is a product. And so we're going to draw energy diagrams that show both endothermic and exothermic reactions. So I'll have an endothermic one here. Time goes on the x-axis, so we see the reaction progress over time, and energy on the y. So for endothermic reactions, looks a little bit like that. That's my reactant, that's my product. So we're going to talk about more of this later. But from where the products are, this little hump here, that is E sub A. E sub A is the activation energy. which is the energy required for a reaction to occur. We will talk more about that later. Then from where the reaction begins, so the R for reactants, up until this line, that's my enthalpy. And you can see from my R to my P, from my reactants to my products, it's going up. So my delta H is positive, and that's why it's endothermic. For an exothermic one, start at the top, have our hump, then we go down my reactants, my products. That's going to be my activation energy, E sub A. And that's my delta H. And from where I start to where I end, it's negative, and that's why it's exothermic. So you should be able to recognize these and to put that information there to determine if it's going to be endothermic or exothermic. Okay, then we've got standard enthalpy of formation. So that was one of those enthalpies in the first part of the notes. It's the energy associated with the formation of 1 mole of a compound from their elements in their standard state at 1 atmosphere and 25 degrees Celsius. Please note that standard state is 1 atmosphere and 25 degrees Celsius. Elements and diatomic molecules have a value of 0. Why? Well, the why is we can't form elements or molecules. We find them like that. So we can take those elements and those diatomic molecules and put them together to form compounds. And so that's how we do a delta H of formation. Now, a state function is a property that does not rely upon a path, but only the start and the end point of the process. Enthalpy is a state function. There are so many ways to find enthalpy. We're going to go over like 3 or 4 of them. We've already did one with Q equals mc delta T. We can do Hess's law, which is states that the overall change for a state function is the same whether the conversion occurs in 1 step or multiple steps, which we'll see on the next page. We can calculate the delta H of the formation. It's going to be equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation for the reactants. So using these enthalpies of formation, we want to calculate the delta H for the reaction. Okay, so the delta H for the RXN, which is the reaction, will be equal to, again, products minus reactants. So products, reactants. So I've got carbon dioxide, so I take the negative 393.5, that's kilojoules per mole. I'm only going to write the units once. There's only one of them, so I don't have to multiply it by anything. Plus 2, because there's 2 of them, the water vapor times negative 241.8. So those are my products, minus my reactants, which are going to be the methane, which is negative 74.81, plus 2 times 0. I'm going to write the 0 just because oxygen, we notice, isn't on this table because it is a diatomic molecule and therefore doesn't have an enthalpy of formation. So you put that in your calculator, and the answer will be negative 802.3 kilojoules per mole. So this shouldn't be an F there, that should be an RXN, so that we can find the enthalpy of the whole reaction by doing the sum of the delta H of the products minus the sum of the delta H of the reactants. Okay, and this is going to be the last slide for today. Now, this is Hess's law. Hess's law allows us to basically, this is the equation that I want. I'm given a series of other equations and their delta H's. I can manipulate these equations and their enthalpies to get that final equation, and then all I have to do is add up the delta H's, and that will give me the delta H for this new reaction. So a couple of things, if I flip an equation, I flip the sign for delta H. If I multiply an equation, I multiply the delta H. If I divide the equation, I divide the delta H. The easiest way to do this, find something that only occurs in one of your reactions from this one. So you'll see I have carbon as a graphite. I only have carbon graphite in this middle equation. So you ask yourself two questions. Do you have the correct number? Is it in the correct spot? So it is a reactant on both, great, and there's one of each. So I'm going to leave that one alone. Okay? Let's see what else only occurs in one of these equations. So I've got methane right there. No, methanol, excuse me. And I only have methanol right here. So you ask yourself, do I have the correct number? Is it on the correct side? I do have the correct number, but I need to flip this. And so what I'm going to do is I'm just going to rewrite it and flip it. Which makes my delta H now positive 726.4 kilojoules per mole. Okay, that's great. And then what do I got here? In this last equation, I have hydrogen. It's only found in this equation. Okay, so I asked myself, is it on the correct side? It is a reactant. Do I have the correct number? No, I need 2. So I'm going to multiply this whole thing by 2. And I'm just going to rewrite it underneath. 2H2 plus O2 gives me 2H2O. And so my delta H is going to be a negative 571.6 kilojoules per mole. So the whole idea is now I can add up all these equations and it should give me that final equation. When I add them up, I cancel things that are the same on opposite sides. I add things together that are the same or on the same side, and then I just add up all my delta H's. So you'll see here, I've got 2 waters here, 2 waters here. So one's a reactant, one's a product. Those go away. Don't want them. What else can go away? I've got carbon dioxide here as a reactant, here as a product. Those can go away. I don't want them. Now, I've got, that equation is not what we're looking at anymore. Now let's see, what do I got? I've got oxygen here. I've got oxygen here. I've got 3/2 oxygen here. So this one's going to go away. This is going to, how's math work? This is going to go away. The 3/2 will go away. And this will turn into a 1/2. So what do I have left? I have C graphite here plus 2H2 here plus 1/2 oxygen here gives me, what's left on this side? CH3OH, which is exactly the equation that I wanted at the end. Then I can just add up all of my delta H's, and that will give me negative 238.7 kilojoules per mole. And that's how you do a Hess's Law problem. The homework assignment will be posted on the Online Learning Week 1 Part 2 Word document. Please have a look on there. There are 2. There's an assignment for heating curve calculations, and then there's an assignment for Hess's Law. Hess's Law, I understand here this looks messy. Try to follow along, go step by step, and pause. If you have any questions, please let me know. Send me an email. If you in the assignment for Hess's Law, there are some easy ones, so try to start off with those. Otherwise, I will see you next week for week 2 of your online learning.